In this video, we're looking at maps. And as we've talked about, the globe is a model of the Earth, and it's probably the most accurate model in showing the size and shape of the Earth. But what it's not really good at is giving you detail. So for instance, if I wanted to know local roads or major highways, I wouldn't go to a globe. I would use a map. And maps are great at displaying specific data, specific topics. And all maps are going to share some basic features. So let's use a map that we're familiar with. This is from your reference table on page 3. And if we look carefully, here's something that all maps share. This is the map scale. Now, maps have to have a scale to show you the relationship between the distance on the map and the corresponding distance in real life on the ground. So because maps can't be life-sized, they have to be scaled. You can use this information to measure the distance between 2 points on a map. If I had a piece of paper or a ruler, I could mark off on my piece of paper the scale. So here I'm keeping track of the scale in miles. And then I could take my piece of paper and I could use now that scale to measure the distance. So let's say I wanted to know how far it was between Elmira and Bigmanton. I'd take the scale that I drew on my piece of paper and I'd measure, and it would be about 45 miles. So this is a great thing to be able to do, and you will need to do it to calculate gradient, which we'll be talking about in class. The wrong thing to do would be to use your fingers. That is not accurate. It's never accurate. Another thing that maps share is some kind of legend or collection of symbols. So in this example, we have different colors on this map. And if we look at the legend that we're given, each color corresponds with a different elevation, height above sea level. The greener colors are the flatter areas, and the browner colors are the higher elevations. Without that information, it would probably be difficult to figure out exactly what the map was trying to communicate. So symbols and legends, very important. And finally, this is something that you can assume for every map unless you're told differently. The top of the page is always going to be the north or going north, and the bottom of the page is always going to be going south. All maps follow that principle. Maps in earth science are going to communicate different types of information. So the map on the left we just looked at, that's a map of elevation. That's a type of map we use in earth science. Weather maps are another type of map we use in earth science. And here's a new type of map. This is called a field map. Now, a field map displays measurable quantities in a three-dimensional space. Maps are not 3D. They're not meant to be 3D, but they are meant to represent three-dimensional space. Common types of fields include air temperature, elevation above or below sea level, air pressure, sea surface temperatures, air pollution. These are all measurable quantities that can be collected and then displayed on a map. This map is showing you air temperature across the United States. This is considered a field because these are measurable quantities. These are actual numbers that were measured by thermometer and written on the map to communicate how temperature is distributed across the United States at a given time. So using this information, we can create isolines. Isolines make reading a field map easier because it displays the relationship among the data points, where the data points are jumbled together or where they're further apart. An isoline connects areas of equal value. Just as there are many types of fields, there are many types of isolines. So for example, these are isobars. They connect areas of equal barometric pressure. Barometric pressure is air pressure. Next, isotherms. That's exactly what we were just looking at. This is using a nice color coding system Isotherms connect areas of equal air temperature. Contour lines. Contour lines are isolines that connect areas of equal elevation. Just to summarize, any region of space or the environment that has some measurable value at every point is a field. And when that data is displayed on a map, we call it a field map. So to create your own field map using isolines, there are 6 steps that we're going to follow. The first step is to identify points of equal value that are shown. Then identify points of equal value that are not shown. I'll demonstrate that in a moment. Connect the points of equal value to each other with a line. Always use a smooth, curved line to connect these values. Never use zigzags or sharp edges. Your isolines can't cross each other because if 2 points cross each other, that means that there's 2 different values in the same place, and that can't exist. And isolines may close to form rounded shapes. This can only be demonstrated, so I'll show you this in a moment. But they can also run off the edge of the map. It just depends on the field that you're trying to show. So here's our sample data. This is a field map plot of temperature. Let's pretend it's temperature in a bedroom. I want to connect the value of 10. So my first step was, let me look for all the 10s. So I have a 10 over here, I have a 10 over here, and those are the only numbers that equal 10 that I can see. My next step is to identify the ones that are not shown. So if these are temperature readings in a room, where would 10 exist, even though it's not being shown with a number on this map? Now that sounds very vague, so let me give you an example. If I'm counting from 9 to 11, so if I'm up here, if I'm counting from 9 to 11, the number in between 9 and 11 would have to be 10. So I would have a value of 10 conceivably there. That same thing would exist here between 9 and 15. If I wanted to count from 9 to 15, I'd have to go through 10. But I wouldn't put my 10 in the middle. I'd put it close to my 9. And the same thing down here. If I wanted to count from 8 to 14, I'd have to go through the value of 10. So once again, I'm going to put a 10 here, represented by a blue dot, because it's not equidistant between 8 and 14. It's not halfway. It's closer to the 8. So now that I have that information, I can draw an isoline. I can connect these points with a smooth curved line. And now I can say anywhere on that line, my value is 10. And I took into account values that were given. These values were given, and hidden values. So let's try this with 15. So I'm going to use a different color for 15. And I'm going to first find my 15s. Here's 2 15s. And those are the only 2 that I'm given. So now I have to think about, where would a 15 be? Well, I know it would be between 14 and 16. I know that a 15 would be between 13 and 16, probably a little closer to the 16. And between 11 and 17, there would probably be a 15. So now that I have those data points, I can connect them with a smooth line. Okay, let's do the same with 20. New color. Here's a 20, here's a 20, 20, 20. Hidden 20s? Well, there'd probably be a hidden 20 there before 21. I think that's it. So now I can connect my points of equal value. Let's go up to 25. And I'll use a new color for that. We'll use the color red. 25 is here, 25 is here, 25 is here, and there are no other 25s. So I have to now think about this. I can't start up here because that's not equal to 25. I can't start over here because that's not equal to 25. I have to start off the page. So I have to come out from the page and connect my 325s and then tuck it back in. And that was one of the rules. I think that was the 5th rule. Or maybe it was the 6th one. That ISO lines, right, they can form closed loops, which none of these do in this case, or they can extend to the edges of the page. So these all extend to the edges of the page. And what I just created was a field map showing my ISO line data connecting points of equal value. This comes with practice. That's it for now, and thanks for watching.